Hello students. In this lecture, I will discuss about combinational logic gates and Boolean expressions of Boolean algebra. Now before going to the combinational logic gates, I'll give you some basic outline about combinational logic circuits and sequential logic circuits. Combinational logic circuit consists of logic gates whose outputs depend only on the present inputs. Output never depend on the previous input. So we can say the previous state of the input or the output does not have any effect on the present state of the circuit. And so because there are no memory element in the combinational logic circuits, that's why there is no effect of the previous state or the present state of the combinational logic circuits, and there is no clock available in these circuits. So clock pulse is not control the operation of the combinational logic circuits, and adder, subtractor, mux, demux, encoder, decoder, etc. are the examples of the combinational logic circuits. And logic gates are the basic elements of the combinational logic circuit. But in sequential logic circuit, there is a memory element which is called flip-flop, and output of these logic circuits depend on the previous input, present input, as well as the past output. So we can say sequential logic circuit consists of flip-flops whose outputs at any instant of time depends not only on the present input but also depend on the past input and past output also. So I have already said that flip-flops are the basic elements of the sequential logic circuit, and it is a memory element. And in sequential logic circuits, actually clock signal determines when things will be happen next. That is, what operation will be the first and what operation will be the next. That is, clock signal control the operations. Counter, register, and other memory elements are the example of the sequential logic circuits. So let's discuss about the basic gates, which is the basic elements of the combinational logic circuits. There are three different types of basic gates. Now, the three basic gates are AND gate, OR gate, and the NOT gate. So, AND gate, it obeys the AND logic, and it is the symbol of the AND gate, and its output is equals to A dot B, that is product of two inputs. So output Z equals to A dot B, where A and B are the input. Now this is the OR gate, and it obeys the OR logic. OR logic is basically sum of the inputs. That is Z is equals to A plus B. And the NOT logic is actually inverse logic, which inverse the input. So the output is inverse of the input, and these are three truth tables of the consecutive gates. So here you can see that since input is 0 and 0, so product is 0. So you can see either one of the input is 0, then output will be 0. When only two or more than two inputs are in the state 1, then and then only output will be the 1. And in OR logic, if any one of the input in the one state, then the output will be in the one state. And you can see in the truth table that for the NOT operation, 0 inverted to the 1 and 1 inverted to the 0. So except these three basic gates, there are also four different types of gates: NAND gate and NOR gate. Those gates are universal logic gates, and also XOR gate and XNOR gate. So let's first discuss about universal logic gates. So from the word universal gates, you must be able to understand that using these two gates you can construct any one of the basic gates. Not only the basic gates, you can also construct XOR gate, XNOR gate, or using any one of the gate you can construct a entire combinational logic circuits. So what is the NAND gate logic? Here you can see NAND gate logic is AND gate plus a NOT operation. So Z equals to first A dot B, then its bar gives A bar plus B bar, which is actually the NAND gate, which is actually the NAND gate logic. Now this is the NOR gate. NOR gate is actually OR gate plus NOT. So here you can see the output is OR operation and its bar equals to A bar dot B bar. Now this is the truth table of the NAND gate, and this is the truth table of the NOR gate. Now this is the XOR gate. So XOR gate is equals to the two input. Output is in the XOR gate, output is equals to A modulo B, which is actually output of the XOR gate. And this is the symbol of the XNOR gate, and the output is Z equals to A modulo B and its inversion. So this is A B bar plus A bar B is the output of the XOR gate, and where A and B are the inputs, and A bar plus B into A plus B bar is the output of the XNOR gate, where A and B are the two inputs. And this is the input, and this is the truth table of the XOR gate, and this is the truth table of the XNOR gate. So this is called the XOR logic, and this is called the XNOR logic. So in the Boolean expression, we have learned about 7 logic: AND logic, OR logic, NOT logic, 2 universal logic, NAND logic and the NOR logic, and 2 others logic, which XOR logic and XNOR logic. Now I will discuss about some basic rules about the Boolean algebra. These are the basic rules of the Boolean algebra. Here I will discuss about these laws, and I will discuss about these theorems in the next class. So first start with to discuss about these laws. Now I am starting the discussing of the basic rules of the Boolean algebra. So here first, these two relations known as the null laws of the Boolean algebra. Now here you can see that in this equation, that is this law states that if any variable ANDed with 0, it gives only 0, that is it gives always 0, and if any variable and ORed with 0, then it gives the variable itself. Now I am showing you by logical gates. Now I am explaining a. Now I am explaining the laws using AND gate. Here you can see A is the input of a two input AND gate and 0 is another input. So this gives the output A dot 0. Now you can see if A equals to 0, then output will be 0. If A equals to 1, then also output will be 0. So the output will be always 0. Now take this relation. So for that I use a OR gate, a two input OR gate. Okay. Now this is the two inputs and this is the output. A is the one of the input. Then now if input 0, then output will be A plus 0. So if A equals to 0, then output will be 0. If A equals to 1, then output will be 1. That is when this is 0, then the output will be 0. When this is 1, then the output will be 1. So here you can see in the second relation, the output will be the variable. Now let's discuss about identity laws. In this identity law, you can see here, in this case, the variable ANDed with 1 gives the variable itself, and in this law, in this relation, variable ORed with 1 gives always 1. These relations also can be explained by a AND gate, a two input AND gate, and a two input OR gate. Now when input is A and 1, then output will be A dot 1. Now when A equals to 0, then output will be 0, and when A equals to 1, then output will be 1. Now see, so it gives the variable itself. Now here in this case, if one input is A and another input is 1, then it gives always 1. How? Now see, if A is 0, then the output will be 1, and if A is 1, then output will be also 1. So output will be always in the on state, that is 1 state. Now discuss about the complementary laws. In this case, you can see, and in this relation, that is, this states that a variable ANDed with its complementary is always equals to 0. Here you can see a variable A ANDed with its complementary always gives 0. That is, now you can see if A is 0, then this one is 1, so which gives the output 0. And if A is 1, and then this input will be 0, so the output will be 0. So this states that output will be always 0 if any variable ANDed with its complementary function. Now, this relation states that a variable ORed with its complement always gives 1. Now, you can see, now if this one in one input and this was another input, so it will give a plus a bar. So if a equals to 0, so this input will be 1. So then this output will be 1. Now if when a equals to 1, then this input will be 0, then also output will be 1. This one is a double negation law. Double negation means a variable is double not operation. That is, a variable is double negation gives the variable itself. So that is two not operation. That is, so when a equals to 0, you can see this will be 1 and this will be 0. When and when a equals to 1, then this will be 0 and this will be 1. So you can see input and output will be the same. Now a dot a equals to a and a plus a equals to a. These are the idempotent laws, and this one states that if a variable ANDed with itself gives the variable itself, and if the variable ORed with itself also gives the variable itself. Idempotent means the same value, and which is maintained by these relations. A ANDed with a gives a ORed with a always gives a. That is, so here you can see if this is 0, this is 0, this will be 0, if this is 1 and this is 1, this will be 1, and here for the same. So these are the commutative laws. That is, here you can see a ANDed b equals to b ANDed a. That is, a and b same as b and a, and also a or b equals to b or a. Now I am just showing you. By AND gate and OR gate. First case a and b. So what is the output? A dot b, which is equals to b ANDed with a. That is b dot a. So if I can show you by truth table. Here you can A B, in this case AB, and this is 0 0 0 0 1 0 1 0 0 and 1 1 1, and in this case B A B dot A. If B equals 0 0 gives 0 0 1 gives 0 1 0 0 1 1 1. Now go to the second one. Two inputs are A and B. So A ORed with B, which is A plus B, equals to B ORed with A, that is B plus A, and this is the truth table of AB. A plus B. You all know the truth table of OR gate, as and I also discussed earlier. B A B plus A. So this is 0 0 0 0 1 1 1 0 gives the 1 and 1 and 1 1 also gives the 1. Here also 0 0 gives the 0 0 1 1 1 0 1 and 1 1 1. Now these are the associative laws. Here you can see B and C ANDed with A, same as A ANDed A and B ANDed with C, and in this case B or C ORed with A, same as A or B ORed with C. That is, you can see, actually this states that the way the variables are grouped, either ORed or ANDed, is immaterial. So B and C associated with A, A and B associated with C, here also the same. Now let me explain this one. B and C ANDed with A, which is gives A and B dot C. So equals to A and B ANDed with C, which is A dot B with C. Truth table for this one, B, C, A. So output will be A. All this is one. A or B. A and B. So you can see actually this one same as this one. Now I explain this relation. So to explain this relation, here AND gates, as I explained earlier, using AND gates, those will be replaced by OR gates. B or C ORed with A, okay, which gives A plus B plus C, which is equals to same as A or B, A or B ORed with C, which is equals to A plus B plus plus C. Now explain it with truth table. B, C, A, B or C, that is B plus C, and now explain this circuit using this truth table. Now I will explain this one here. Now the truth table is A, B, C, A plus B, A plus B plus C. Actually, this A and B gives this also. Now this gives. So here you can see this truth table same as this one. So A or B or C equals to A or B odd with C. Now let's discuss about this relation. These are called the distributive law, where you can see A ANDed with B or C is equals to A and B odd with A and C. And here you can see A odd with B and C equals to A or B ANDed with A or C. Now first I will discuss this relation by logical gates, and then I will discuss the relation using logical gates. So first discuss this. So here you can see B or C ANDed with A. So B or C ANDed with A. So here you can see A and B plus C, that is B or C, equals to, it is same as what? It is same as A and B with odd A and B so A and B odd with A and C, which gives A dot B plus A dot C. Now let me discuss this circuit using truth table. So here you can see B and C are odd together. So this is the A ANDed with B and C. Now let's discuss. So this gives this one, and now discuss this circuit using a truth table here. So AB is, so this portion is this one, and this BC, sorry, and this A and C gives AC. So AB is 0, AC is also 0. So this explains this circuit. Now let's discuss about this equation, that is this relation. So before going to this relation, explaining this relation, I am telling you that this relation, that is this law applies to single variable as well as combination of variables, and also this is true for this one, that is this is also true for combination of variables. Now I am showing you use this relation using logical gates. B and C ORed with A, which is equals to A plus B dot C, equals to A or B ANDed with A or C, and this is equals to A plus B dot A plus C. Explain this logical circuit by a truth table. explain this circuit by another truth table here. So AB is this A and B, and A and C is a AC. So that is this and these truth table are the same. So now this relation and this relation can be explained algebraically. Now here you can see equals to A dot A plus A dot C plus B dot A plus BC. Now equals to A dot A equals to, you know that A dot A equals to A, so plus A dot C, that is AC, plus we can write B dot A equals to AB plus BC, which is equals to A into 1 plus C. So this one is 1 from this relation, which is equals to A plus BC. It's actually proved. Now let's discuss about the law of absorption. That is, you can here you can see B is absorbed. Here also B is absorbed. So you tell this is the law of absorption. I am explaining this one by logical gates. Here you can see. And now see, first relation states that A or B ended with A. So here A or B ended with A. So this is A dot A plus B. So the truth table is A, B, A plus B, and then so here you can see that A plus A or B ANDed with A gives the variable A itself, where B is absorbed. So here you can see if 0 is 0 gives 0, 0, 1, 1. That is the OR operation. 1, 0, 1, 1, 1, 1. So this gives 0, 0, 1, 1. So here you can see this line is same as this line, that is the A is equals to this one. Now I am explaining the second one, this relation. This relation, that is, in this relation A and B ORed with A, which gives the A where B is absorbed. Now A and B ORed with A, that is A plus AB. So the truth table is first and get truth table. So here also you can see this column is same as this column, that is A equals to this, and this is called the law of absorption. And this can be also proved by a logical by algebraically, and do it yourself. So now let's explain the last one, that is the law of common identities. And I have already said that I will discuss those theorem in the next lecture. So law of common identities, here you can see A bar means negation of A or B ANDed with A gives AB. And in the second one, in the second case, negation of A and B ORed with A gives A plus B, and this is called law of common identities. And here I am explaining this one by logical gates. Now see, A bar or B ANDed with A. So A bar or B means A bar or B ANDed with A. So A dot A bar plus B, which is equals to so let's explain this circuit by truth table, and this is the truth table of the AND gate, you know. Now A, B, A bar plus B, A dot A bar plus B. So here you can see this is the truth table, this is the output of the AND gate. Now I am explaining this relation. So here A bar ANDed with B, then ORed with A, which gives A plus A bar B equals to A or B. A or B. Now let's explain with a truth table. It is also easy one. A, B, A bar B, A plus A bar B. So this signifies the output of a OR gate. So here you can see, students, I have explained all the laws by logically, that is the logical, using logical circuits and truth table also, and also some of the relations can be explained algebraically. Now I'll discuss about those theorems, consensus theorem, transmutation theorem, and De Morgan's theorem, and some other theorem in the next lecture. Thank you guys. God bless you.